Assalamualaikum. My name is Nur Atira binti Ahmad Tamrin. My metric number is 08DJK22F1014. Okay, so today I want to introduce about integration. Integration help us in finding the areas of the two-dimensional region and also help in calculating the value of three-dimensional objects. Therefore, finding the integral of a function with respect to x means finding the area to the x-axis from the curve. Okay, this is an example area under the curve formula. The area under a curve between 2 points is found out by doing a definite integral between the 2 points. To find the area under the curve y equal fx between x equal a and s equal b, integrate y equal fx between the limits of a and b. This area can be calculated using integration with given limits.
Assalamualaikum and selamat sejahtera. My name is Nurul Ismira binti Syamsuwarin. My number metric is 08DJK22F1021. And the question is, find the area of the region bounded by y equal 3x minus x and the x-axis. Okay, first, try having a look at this function out here. 3x minus x square. Okay. Okay, x we in the bracket 3 take away x. We can get from the factor, and you get x equal to 0. From the 3 minus x factor, and you're going to get x equal 3 and your x-intercept. Okay, first, so I need some boundaries. I need a lower boundaries, and when do I start, and I need an upper boundary when I end. Area I need define integrate here. So we go lower is 0 and the higher one is 3. We usually say upper. Okay, so 3x take away x square, and then I go with this. Okay, next this is going to become in the square bracket 3x square, and we divide by 2 and then take away x cubed on 3. Close bracket and integrating 9, 0 and 3. So I get 3 times 3 square on 3 on 2 take away 3 cubed on 3, and this becomes 0 take away 0 and close bracket. So let's actually start simplify, and 3 times 3 square is 27 over 2, and then I got 27 over 3 take away 0. I got a factor, I got of 27 off, a half take away a third. So I got 27 divided by 6, and I can simplify that one more time because there are common factor of 3 on the 2 pen buttons, so that's me 9 over 2 unit square. Thank you.
Okay, for the next slide is about question about application of integration to find area. What is application of integration to find area? Is one of the use of integration is to find area. For example, a civil engineer might want to know the area of piece of wood used to do from work to build an architect of a building. A fashion designer might want to know total fabric area needed to make a curtain. This example. So for my question is, calculate the area under the curve of a function. It given at s equals 7 minus x squared. The limit is given as s equal -1 to 2. Okay, for the next slide is the calculation how we find the area. So area equal integrate to -1 in bracket 7 minus x squared dx. Okay, when we have the integrate, we must remove the dx, and the number of integrate we put at the back of the bracket. So equal in bracket 7x minus 1 per 3 x cubed to -1. Okay, for the second step is we put the upper value of the integrate in the s for the equation, for the first equation. So 7 multiply 2 multiply 2 minus 1 per 3 multiply 8. And then for the second bracket is minus 7 multiply -1 minus 1 per 3 multiply -1, because -1 is the value of the is the lower value of the integration. So when we put all the value in the calculation, we can get the value is 42 minus 8 per 3 minus 1 minus 21 per 3. So we get the 34 plus 20 per 3, and the final answer is the answer is 44 per 3, and the final answer is 80 square unit, because it is square because it's in the area. Area is, we must put the square, not the cube, because the cube for a volume. Okay, so we get the answer is 80 square units. Okay, that's all for this equation.
Good day to Miss Lee Ten, and today me and Shazwan will be presenting about application of integration to find volume. Integration can be used to calculate areas. In simple cases, the area is given by a single definite integral, but sometimes the integral gives a negative answer, which is minus the area, and in more complicated cases, the correct answer can be obtained only by several parts and adding or subtracting the appropriate integrals. One very useful application of integration is finding the area and volume of the curved figures that we couldn't typically get without using calculus. Since we already know that we can use the integral to get the area between the x-axis and y-axis and a function, we can also get the volume of this figure by rotating the figure around either one of the axes. The question is, find the area bounded by the curve y equals to x to the power of 2, the x-axis, and the vertical line x equals to 2. To find the area bounded by the curve, the x-axis, and the vertical line, we can set up the integrals as follows. Y equals to x to the power of 2, and the vertical line is x equals to 2. Then we need to find the values of x where the curve intersects the x-axis. Setting y equals to 0 in the equation y equals to x to the power of 2, we find that x is equal to 0 is the x-intercept. Integral to find the area is given by the symbol 0 to 2 fx dx. Putting in the value, it becomes integral 0 to 2 x to the power of 2 dx, and to integrate x to the power of 2 with respect to s, we get 1 over 3 times x to the power of 3. Evaluating the integrals at the limits of integration. A equals to 1 over 3 times x to the power of 3, evaluated from 0 to 2. A equals to 1 per 3, and times it by 2 to the power of 3 minus 0 power of 3, and we get a equals to 1 over 3 times 8 minus 0. The final answer is 8 over 3 square, or 2.667 square.
Okay. Now my question is, find the volume of the solid obtained by revolving the region M around the x-axis. Volume equal the integral x equal a to x equal b, because we are revolving around and we are to across, so that why we need everything in terms of x, so it be our area in terms of x ds, and that area is the of one cross section, so this cross sections circle, we know the formula for that is pi r square. So our volume is going to be from s equal 3 to 7, because those are the area is pi r square, and we figure out what r is going to be in a second ds. Okay, this doesn't seem so bad. So we can see that there are a bunch of different size of circular discs here, and those are changing as we move along the interval, but what's consistent is the height, is the radius of this. You can see that the radius is from the x-axis, which is the middle C. If we can draw a point in, so the x-axis all the way to the line which we can is equal the square root of x minus 1. So that height is y, which is the square root of minus 1. Therefore that's our radius. So it becomes the integral of from 3 to 7 pi r is the square root of x minus 1. No matter where we are in terms of x squared ds, and we just square it because the radius is squared. So this will be the pi can come out from the need to grow 3 to 7 of x minus 1 when we take something under the square root and square it, the square just this separate x. And now we are ready to integrate its pi into x squared over 2. That's the integral of x minus x evaluate from 3 to 7, which will be pi into plug the 7 in first. So 49 over 2 minus 7 minus plug the 3 in 9 over 2 minus 3, and we get the pi into 49 over 2 minus 9 over 2 is 14 over 2 minus 7. 3 is minus 4. So this is so minus 4 is 16 pi units cube.
Okay, after we see all the example of the application of integration to find area and to find volume, we know that integration is a mathematical technique to calculate the area under the curve. There are multiple methods of integration, of which we explore integration by part in this article. So here we derive its integration by parts formula and also understand its application. Okay, so I think that's all for me and from all my group members. So thank you.